Hello everyone, welcome to my channel GVS Chem. In this module, let us discuss thermodynamics, Hess law and its applications. Please subscribe to my channel, like, share and comment on my videos. On the basis of numerous thermochemical observations, the Russian scientist Henry Hess gave one of the most important generalizations of the thermochemistry, and this generalization is referred as Hess law after his name. Now the statement is read as, if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reaction into which the overall reaction may be divided at the same temperature. Let us try to understand this by taking an example. Say here in this a reaction takes place from A to B. So the reactant here is A to B. So this is A to B is the path 1. Path 1. Instead of converting this reactant A to B, in the second path it may be, in the first step it converts A to C, then it converts C to B. So here the enthalpy changes here, this is delta H, and here from A to C this is delta H1 and here delta H2. According to the Hess law of constant heat summation, delta H is equal to delta H1 plus delta H2. So here this is the A to B is the overall reaction. The overall reaction is divided into two steps at the same temperature. The first step is A to C and the second step is C to B. Now let us illustrate this with one example. Now in this reaction let us find the enthalpy change for the formation of carbon monoxide. So delta H for carbon monoxide. So this is C graphite, because graphite is the standard state of element carbon. So C plus O2 gives CO. This is gas. So here enthalpy change, this we have to find. Because why we cannot find? Because when the combustion of coal takes place, combustion of carbon takes place, though carbon monoxide forms, but still certain amount of carbon dioxide also forms along with the carbon monoxide. Therefore, enthalpy change for carbon monoxide cannot be found directly from this reaction. Therefore, we can find the C plus O2 gives, this is gas and of course this is graphite. We get CO2 directly. So here the enthalpy change is given as minus 395.5 kilojoule. Now already in here we conducted the reaction between graphite and oxygen and of course we get carbon monoxide. And you know that carbon monoxide further undergoes combustion to form carbon dioxide. So this is carbon dioxide gas. So here delta H, this is, let us say this is delta H2 is equal to minus 283.0 kilojoule. Now here according to Hess law, so by Hess law, delta H is equal to delta H1 plus delta H2. So delta H how much here? Minus 390.5 is equal to delta H1. This we have to find plus delta H. This is minus, no? So let us keep minus here. So this is minus 283.5. Therefore, delta H1 is equal to 10 minus 3, 7. So this is minus 107 kilojoule. Thus, the enthalpy change for the reaction, that is C plus O2 gives carbon monoxide, is found as 107 0.0 kilojoule. Applications of Hess law. Hess law is applied in determining standard enthalpy of formation and enthalpy of transition and standard enthalpy of reaction and others, wherever it is not possible to make such calculations. Therefore, the first application is determination of standard enthalpy of formation. Many substances like methane, ethane, benzene, C6H6, methanol, CH3OH, etc. For many substances, they cannot be synthesized directly by using elements. Therefore, enthalpy of formation is not possible to determine directly. In such cases, the enthalpy of formation can be found indirectly by using the Hess law. Let us illustrate this with one example. Sulfur plus oxygen gives sulfur dioxide gas. This is gas and of course this is solid. Therefore, here delta H1 is equal to minus 297.4 kilojoule. Now on the other hand, this is here delta H. This delta H is referred as enthalpy of reaction or enthalpy of formation also. Because enthalpy of reaction, this is also referred as enthalpy of combustion. This is also referred as enthalpy of formation because sulfur dioxide is obtained directly by combining elements. On the other hand, SO2, sulfur dioxide gas, combines with oxygen, burns, and of course we get, this is here half molecule, we get SO3. So here we call it as a combustion of sulfur dioxide. Therefore here delta H2 is equal to minus 97.9. So if we add these two equations, S sulfur solid plus oxygen 1 plus 1 by 2, this is 3 by 2 oxygen molecules. Sulfur dioxide and left side and right side cancelled, therefore we get SO3. Since these two equations we added, therefore the enthalpies of reactions also can be added. Therefore delta H is equal to delta H1 plus delta H2. Therefore delta H formation for sulfur dioxide equal to minus 297.4 minus 97.9. Therefore the answer here is minus 395.3 kilojoule. So this is the enthalpy of formation of sulfur dioxide. So since enthalpy of formation of sulfur trioxide. Since sulfur trioxide cannot be obtained directly from elements, therefore we found by this indirect method. By using Hess law, enthalpy of transition can be determined. Enthalpy of transition means conversion of one allotropic form to another allotropic form. So, for example, phosphorus, red phosphorus to yellow phosphorus. So, these two are allotropic forms of phosphorus. Similarly, sulfur, rhombic sulfur to monoclinic sulfur. Rhombic sulfur to monoclinic sulfur. Of course, these are the transitions, allotropic transitions. So, these allotropic transitions cannot be found directly by using the experiment because the enthalpy change involved is very, very small. Very, very small. Therefore, indirectly we can measure. Now, let us illustrate this with one example. So, here let us find out the enthalpy change for rhombic sulfur to monoclinic sulfur. So, first of all, combustion of rhombic sulfur. S R means rhombic plus it combines with oxygen. So, sulfur burns in oxygen and we get sulfur dioxide gas. Therefore, delta H1 is equal to minus 295.1 kilojoule. Similarly, combustion of monoclinic sulfur. Combustion of monoclinic sulfur. So, sulfur, monoclinic sulfur plus oxygen gas gives how much this is? SO2 plus delta H2 is equal to minus 296.4 kilojoule. So this is equation number 1, equation number 1, equation number 2. So if you subtract number 2, subtract equation number 2 from 1. If you subtract equation number 2 from 1, so this is S rhombic minus S monoclinic. And of course oxygen get cancelled, and here also sulfur dioxide get cancelled. So this is equal to, how much this is? Delta H1 minus delta H2. Delta H1 is minus 295, this is 0 here, minus 295.1 kilojoule, minus of minus plus minus 296 point. This is nothing but how much we get here? This value plus 1.3. So here if we bring this S rhombic gives S monoclinic. Therefore enthalpy change is delta H equal to plus 1.3. Since this is very small, it cannot be found directly by converting rhombic sulfur to monoclinic sulfur. Therefore Hess law is used here. By using Hess law, we can find the enthalpy change of a reaction, that is standard enthalpy change of a reaction. So the standard enthalpy change delta R H naught is equal to sum of the enthalpies of formation of products minus sum of the enthalpies of formation of reactants. So change in enthalpy of a reaction is equal to sum of the enthalpies of formation of products minus sum of the enthalpies of formation of reactants. Therefore this can be written as delta R H naught is equal to sigma represents sum, sigma enthalpy of formation of products minus sigma delta HF reactants. So based on this we did problems in the previous modules. Now let us discuss the enthalpy changes for different reactions. Suppose a substance dissolves in solvent, say water. Certain amount of energy may be released, may be absorbed. For example, when sodium hydroxide dissolves in water, NaOH, aqueous. So here heat releases. Very large amount of heat releases so that water may boil. When other substance, that is ammonium chloride, is dissolved in water, we get ammonium chloride Cl, aqueous. When ammonium chloride dissolves in water, heat is absorbed. That is, if you touch the test tube or beaker where ammonium chloride is dissolved, you feel cold. Whereas the test tube or beaker in which the sodium hydroxide dissolves, you feel hot. So when substance dissolves in solvent or water, energy changes takes place. So this energy is known as a standard enthalpy of a solution. So the standard enthalpy of solution is the enthalpy change accompanying the dissolution of 1 mole of a substance in a specified amount of a solvent under standard conditions. Now when ionic substance dissolves in water, there are two types of energy changes takes place. When ionic substance dissolves in water, first of all, solute-solute interactions break. That means ions are separated from each other. Once ions are separated, then other change takes place. See, during this solute-solute interactions breaking, lot of energy is required because there is electrostatic attractive forces. To break these electrostatic attractive forces, energy is taken to break the solute-solute interactions, and of course this energy is also referred as a lattice enthalpy. When solute-solute interactions are broken, then what happens? Solute new bond develops, new attractions develop, solute-solvent interactions develop. When solute-solvent interactions develop, and during this development of solute-solvent interactions, amount of energy liberates, which we call it as a solvation. Now, so the energy required to break the solute-solute interactions is known as lattice enthalpy. So when ionic substance dissolves in water, solute-solute interactions break, and this lattice enthalpy is the enthalpy change taking place when 1 mole of an ionic compound dissociates into gaseous ions of opposite charges at the standard conditions. Now let us take an example. So when Na plus Cl minus, which is in solid state, so this solid sodium chloride breaks Na plus gas plus Cl minus gas, and of course here delta LH. Delta LH means lattice enthalpy. This is plus 788 kilojoule per mole. So when solid sodium chloride dissociates into its constituent ions in gaseous state, it takes 788 kilojoules of energy. That is, it is endothermic reaction. Or otherwise, or we can write this reaction in another manner. Na plus G plus Cl minus G gives NaCl. Delta LH equal to minus 788 kilojoule. Therefore, lattice enthalpy is the amount of energy releases during the formation of 1 mole of solid ionic substance from its gaseous constituent ions. Now, once these ions are separated, then what happens? Solute-solvent interactions take place. So, enthalpy of hydration. This is solute-solvent interactions. Solute-solvent interactions. Enthalpy of hydration is the amount of energy released by hydration furnished by 1 mole of ionic compound. That is, these ions, so sodium ions and chloride ions, are surrounded by solvent molecules. So, as solvent molecules surround, this is known as enthalpy of solvation. If water is used as solvent, this is known as enthalpy of hydration. Now, so the relation between enthalpy of solution, lattice enthalpy, and enthalpy of hydration can be shown here in this manner. So this is AB solid changes to constituent ions AB, A plus and B minus. Here the energy required is referred as enthalpy of solution. AB solid dissociates into its constituent ions in gaseous state. Therefore, here the energy is taken out, and this energy is known as lattice enthalpy. The so released ions are surrounded by solvent molecules. Therefore, this is energy of solvation or enthalpy of solvation. If water is used, it is called enthalpy of hydration. Therefore, delta H solution is equal to lattice enthalpy plus enthalpy of hydration. Enthalpy of hydration. Just now we discussed about the lattice enthalpy. It is the amount of energy releases during the formation of 1 mole of solid ionic substance from its constituent gaseous ions. So that is lattice enthalpy. Lattice enthalpy cannot be found directly by using experimental techniques. Therefore, this lattice enthalpy can be found by an indirect method, that is by using other reactions, and of course this cycle of reactions or equations developed by two scientists, Max Born and Fritz Haber. Therefore, this is referred as a Born-Haber cycle. Born-Haber cycle is nothing but an application of Hess law of constant heat summations. Now, let us take sodium solid plus chlorine gas. Sodium solid, chlorine gas combine, and we get NaCl solid. So here enthalpy of formation of sodium chloride is equal to minus 411.8 kilojoule per mole. 8 kilojoule per mole. So this is the enthalpy of formation of sodium chloride. During the formation of sodium chloride, many energy changes take place, and these energy changes, different energy changes take place during the formation of sodium chloride. Let us discuss now. First of all, sublimation of sodium atoms. Sublimation of sodium atoms. Na solid changes to Na gas, and here delta H sublimation. Delta H sublimation is equal to 108.4 kilojoule. So when sodium solid changes to sodium gas, energy is taken, and of course this is known as enthalpy of sublimation, that is 108.4 kilojoule. Sodium gas changes into sodium ions. So gaseous sodium ionizes into gaseous ions. Therefore we get the energy involved here is enthalpy of ionization, and this is 495.6 kilojoule per mole. Next step, chlorine, atomization of chlorine. Here chlorine molecules are available. These chlorine molecules are to be dissociated into chlorine ions. So this is chlorine gas. Therefore here delta AH. Delta H, AH means atomization, enthalpy of atomization. So here enthalpy of atomization, here only half molecule is involved, therefore we take delta HA, this is ClCl. So this is equal to 121 kilojoule per mole. 121 kilojoule per mole. And the fourth one is this chlorine takes an electron. Chlorine takes an electron, and we get chloride ion. Chloride ion. So during formation of chloride ion, certain amount of energy releases. Therefore this is delta EGH. EG means electron gain. Enthalpy of electron gain enthalpy is nothing but minus 348.6 kilojoule. And finally lattice enthalpy. Lattice enthalpy means enthalpy change taking place during the formation of 1 mole of solid ionic substance from its constituent gaseous ions. Therefore Na plus gas plus Cl minus gas, we get Na plus Cl minus solid. So here lattice enthalpy, this lattice enthalpy is only we have to find. Now according to the, as per Hess law of constant heat summation, we can add all the enthalpy changes discussed just now. So enthalpy of formation is equal to enthalpy of sublimation plus enthalpy of ionization plus enthalpy of atomization plus enthalpy of electron gain enthalpy plus lattice enthalpy. Now let us substitute all the values in this equation. So this is minus 411.2 is equal to 108.4 plus 495.6, and enthalpy of atomization 121, electron gain enthalpy, this is minus 348.6, and of course lattice enthalpy we have to find. Now let us make the algebraic sum. So minus 411.2 is equal to, if we add all these positive values, we get 725.0, and this is plus into minus 348.6 plus delta enthalpy, lattice enthalpy. So here minus 411.2. So this is plus and this is minus. So if we subtract 348.6 from this value, we get 376.4 is equal to lattice enthalpy. So bring this to this side. Lattice enthalpy equal to minus 411.2 minus 376.4. Therefore, this is nothing but minus 787.6 kilojoule. Therefore, this much amount of energy releases when gaseous ions combine or come closer to form solid ionic substance. Therefore, this is lattice enthalpy. Lattice enthalpy of sodium chloride is minus 787.6 kilojoule per mole. So, all these changes can be shown in a diagrammatic representation, that is Born-Haber cycle. So, till now we discussed about the different reactions take place in Born-Haber cycle. So, this is the schematic diagram for Born-Haber cycle for sodium chloride. Here sodium solid plus half Cl2 combine and we get sodium chloride solid. So, here this energy change minus 411.2 is enthalpy of formation of sodium chloride. Here sodium solid changes to sodium gas. Therefore, this is the enthalpy of sublimation of sodium, that is plus 108.4. Sodium gas changes to sodium ions in gaseous state and enthalpy change taking place here is plus 495.6 and this is referred as ionization enthalpy. On the other hand, this is half sodium chloride converts into sodium atom, sodium chloride molecule converts into sodium atom, and here energy change taking place here is 121. Therefore, this is enthalpy of atomization. And during this chlorine atoms take one electron and become chloride ions. Therefore, here electron gain enthalpy is minus 348.6 kilojoule per mole. Therefore, this is electron gain enthalpy, and finally this is lattice enthalpy. Therefore, we write once again here enthalpy of formation is equal to enthalpy of sublimation plus enthalpy of ionization, that is, or ionization enthalpy. So this is ionization enthalpy plus enthalpy of atomization for chlorine, and this is electron gain enthalpy plus finally lattice enthalpy. So we discussed this summation already. Therefore, lattice enthalpy of chlorine we obtain as minus 787.6 kilojoule per mole. In the next module, let us discuss the enthalpy of neutralization and bond enthalpies. Please subscribe to my channel, like, share and comment on my videos. Thank you.